Hello everyone. In this computer lab, we'll do some next-generation sequencing read mapping and the downstream analysis, variant calling. This computer lab will continue for 2 days, today and tomorrow. Today we'll talk about short-read aligners, do a comparison between BWA and Bowtie2, and do an introduction on variant calling, and do a variant call by BCF tools. Tomorrow, we'll talk about GATK best practice for variant call, including the data pre-processing and the germline SNP and indel color. And we'll also do some functional annotation. So first, please connect to OSC ovens and make sure to copy all the lab materials in the DNA-seq folder into your directory. Now I already connected to ovens and I'm in my home directory. Now I need to go to the project directory. PS1669. And now I can see there is a DNA-seq folder. I want to copy and paste, do a rsync this directory to my own directory here. OSU10655 is my username. Okay, it took about 1 minute to transfer over 16 GB files. And now let's make sure you are in the, you are in the DNA-seq folder inside your own folder. Then you will look at, you will have 2 directories and 1 file. In that particular setup comments file, you can look at it by last command. And you can run the following module commands every time you open a new terminal window or before this computer lab, because you don't need to load every software one by one each time when you need to use it. I just copy and paste. Okay, BW and Bowtie2 are for the alignment, and the BCF2 is, and the PCAR is for the variant call. SAM tools is very useful basic tools for manipulate SAM file, and R subread and SNP if is what we're gonna use in the following labs. Okay. So the first folder, Ebola, is what we're gonna use today, and the GATK workshop is what we're gonna use for tomorrow. Let's go to the Ebola folder and take a look. There are 2 shell scripts what I used to get the reference genome and FASTQ file from NCBI. In the refs folder, there are some, there is one Ebola genome FASTA file, that is the genome reference for Ebola virus. And in the data folder, I have downloaded 1 set of reads from the SRA and the 2 sets of reads. The red one is what I simulated by myself according to the virus genome reference file. The first set has error rate 0.1, that is 1% error rate, and the second set is 10% error rate. So let's start on the alignment. Before we start the alignment, we can index our reference FASTA file. It's always convenient to index the FASTA file so we can view it in some genome browser. We can use SAM tools, FASTA index command to do the index for this af.fasta file. Okay, it's done. So if I don't want to every time type in this refs af number.fa file, I can just assign it to a variable ref. And then we can do the index with BWA. Let's first check what BWA comment has. The index one is index sequences in the FASTA format. That is what we need. And the MEM is WA MEM algorithm. That is we're gonna use for the short array alignment. And if I want to know how to use BWA index, I can just type in the command and use enter. And then it will show, like, I can just put input FASTA file here. So that's what I'm gonna do. The input FASTA will be the in the ref variable. Now, the index is already built for BWA. So we can take a look in the reference folder. Besides the FA, let me align it in a time order. First, we already have the FASTA file there, and the file ending with FAI is the index for this FASTA file. It's much smaller than the FASTA file. And then the 5 files ending with some weird letters is the index for this FASTA Geno FASTA file. And those are binary files, so we cannot view it. Next, let's do the index for bowtie 2. We can also similarly to check what bowtie 2 command has how to use it. So bowtie 2 and the bowtie 2 build is the command to use for building an index. So it's just a reference file, input file, and then the index space. So the input file and the reference index base are gonna use the same base. Okay, now it's done. Let's look at the refs file folder. The last 6 files ending with BT2 are the index file for bowtie 2. Okay, after the first step, the index building step, now we can align our short rates. Let's first use the simulated rates with 1% error rate. Those rates are in the data folder and with 1% error rate. Read 1 and read 2. Okay, now we can use BWA MEM command. First is the reference index, and then is the read 1, read 2, and the output, let's name it BWA SAM. And I want to time it because I want to compare BWA alignment speed and mapping rate. So it took about 5 seconds to finish the alignment. Now let's look at the timing for the bowtie 2 alignment. The index base name, read 1, read 2, and the output, let me call it bowtie2.sam. So Bowtie 2 will give you an output about alignment rate. But this output, for me, I think it's not very easy to understand. There is a 94% overall alignment rate here. And the time is 15 seconds. It took a longer time. And for mapping rate, I will compare it with BWA later. First, I want to explain a little bit about this output. It means there is 100,000 reads that are paired. So we can say there are 100,000 fragments, and in one fragment, it has 2 reads. And the distance between the 2 reads should be in a well-defined range. It cannot be over 10,000. It should be reasonable. Depends on library preparation. I would say it's something between 200 to 400 base pair. And out of this 100,000 paired reads, there are 52,000 aligned 0 times, that is not aligned, and 47,000 aligned once. So 40,000 fragments aligned once. So 40,000 times 2, about 80,000 or 94,000 reads aligned once. And out of those pairs that not aligned concordantly means it's not only uniquely mapped, but also the distance between the 2 reads satisfy the pair and read rule. Out of those 47,000 aligned disconcordantly once. Disconcordantly means each read in this fragment, each read mapped uniquely, but the distance between these 2 reads are either too long or too short, so that doesn't make sense. It means mapped discordantly. And then out of those that is not aligned either concordantly nor disconcordantly, those pairs are made up, those fragments are composed by 10,000 reads. Out of those 10,000 reads, there are 293 aligned exactly once. So if you want to get this 49% overall alignment rate, that means this number times 2 plus this number plus times 2 plus this number, and divided by the total reads. Okay, and there is a easier way to look at the mapping rate is by the SIM tools. Flag stack command bwa.sim. This one is 95% alignment rate. And let's look at the Bowtie 2. This one is 94%. When the error rate in the read is 1%, both BWA and Bowtie 2 perform quite similarly. BWA has a slightly better overall map rate and speed, but I would say the performance between these two are very similar. Now let's look at the read with higher error rate. Okay, this time BWA took 8 seconds to finish. And the alignment rate is 83%. Now let's do bow tie 2 again. Okay, we already see the overall alignment rate is dropped a lot for bow tie 2. So it's 29%. Based on this example, the property of the input data have a big impact on both runtime and mapping rates. But does it mean that bow tie 2 is a second citizen in the aligners, short rate aligners? Maybe that we draw this conclusion too early. We can tune bow tie 2 a little bit. You can copy and paste the command from my tutorial. Now let's set it in the very sensitive local mode and let's see what's the result. We just make it more sensitive, so it's gonna take a slightly longer time than before. And by the way, by default, bow tie 2 is using the sensitive local, and now it's a very sensitive local mode. This time it took 21 seconds, and it's a 64% overall alignment rate. Let's tune it a little bit more. This time we identify the dash D, R, N, and L parameter. We set those parameters similar to very sensitive mode, but change the N parameter from 0 to 1. And this time we got a much better overall alignment rate, 87%. It's even better than BWA. But here I have two questions for you. What those parameters mean? You can look at it just by looking at the bow tie 2 manual. And the second question is, does it always mean the higher alignment rate, the better performance? If I develop a liner, give you 100% alignment rate, no matter what the input file is, do you want to use this aligner? Okay, yeah, that's the two questions for you to think about. And this comparison example give us two take-home message. First, it's not that simple to compare aligners. Sometimes even one aligner, the same aligner like BWA, it uses different algorithm over different time period. So it's really not that simple to compare them. And when you read the benchmark papers, you have to pay attention to those details. And the second, if you really want me to recommend a DNA sequence read aligner to start with, I would recommend the BWA. And the BWA MEM algorithm is pretty robust and is always a good starting point.